Good morning, everyone. Thanks for inviting me here to talk about my research. Today, my talk will cover two perspectives of things. The first one is on the structural controllability theory, and also maybe a little more on the functional controllability as well, which may be a little different from what I propose. As we know, human being lives in a very complex environment. One has to do a lot of things every day. For example, one has to eat, to work out, to learn, and to rest. Instead of staying rigid and inflexible, the brain has to process the incoming information, alter its behavior to adapt to its incoming goal and inhibit the unwanted state. This ability of alternation and adaptation is called the cognitive control. So our problem here is we want to come up with a framework, both from functional and structural perspective, to explain why some regions are playing a more important role in this process of cognitive control. Our motivation comes from some of the engineering control, where to arrive the target state or the reference, we have to measure the system's current state and use a controller to design certain kind of input to alter the system's current state towards what it wants. And for the brain, we have an analog to the similar thing, where to change from one state, for example, the steady state, to the restless state. Then the target state would be the restless state, and at each time the brain may be between something for these two ends, and some system or some area of the brain generates some intrinsic signal to tune the brain's current state, so that at some time it will change the task from study to rest. Or more graphically, for the brain, we want to do such a kind of thing. From some modeled or data-driven recognized states towards some target state, we want to alter or iterate the possibility of control area and design certain kind of control form so that the brain's state transition task can be performed, and we can have an approach to analyzing the property of associated energy as well. When we talk about networks, usually, especially the brain network, we refer to two things. The first one is the structure connectivity, where the connectivity among regions are measured by the streamlines, and for the functional controllability and functional connectivity, where the links are defined as certain kind of statistical association, for example, correlation, coherence, causality, and so on. For the structure controllability framework, we modeled it as a very simple dynamic system, which is linear discrete time and time invariant network model. The state of the brain at time t+1 is modeled as its transformed state from time t plus the control term. In this equation, the transition matrix A is utilized as the structure connectivity matrix, and the BK represents where we have the input, and the UK represents the exact form of the input energy. With this setting, we can then define two quantities. The first one is called the T-step controllability matrix, which is defined as a concatenation of control design matrix BK and the transition matrix A. This one represents how controllable the system is. If the system is controllable, which means we can drive it from any initial state to target state, then this CK then the situation is equivalent to the full rank of the CKT matrix. The second one is the controllability grammar, which represents how controllable the systems are. which means that if the system costs more energy to achieve a certain state transition, then this quantity would be higher. Based on the two measurements, we define two kinds of controllability measurement. The first one is called the average controllability. Mathematically, it's defined as a trace of the Gramian inverse, which intuitively it measures from an initial state to its 1 unit distance away state. In average, how much energy will be cost. In the application, this one tends to find those regions that are highly connected to the others. And if we quantify from a system level, the hubs of average controllability, which means that the regions with high average controllability values tends to accumulate in the default mode system, which suggests that the Brownian's baseline might be optimized to allow one to move a system to arrive at many easily reachable states, because this will come up with a higher efficiency of energy using. Oops. And the second one is the model controllability, which is defined as the weighted average for eigenvalues and eigenvectors, which quantifies almost the opposite thing of the average controllability. This one pays more attention to the worst situation, in which if the energy cost of driving a state from its initial to 1 unit distance away, if the worst situation costs the most energy, if the energy cost in the worst situation is higher, then this model controllability would be of a higher value, which shows that, which is more likely to accumulate in higher level system, and suggests that the cognitive control area are called when one needs to make a difficult transition between different tasks. This is because to move the brain to some difficult to reach state, or to change the values, or to change the activation at some weakly connected area, the optimal strategy may be simply changing the values on spot instead of drive it from somewhere else, if you want to do it very accurately. Okay, the above is is a summary of our structural controllability work, and the following slides is more on the functional one. For the structural one, the most important assumption is on the transition matrix, where we assume that it's constrained from the structural connectivity, which is built from the streamlines or topographies. And for the functional network, since we have those time series, we can actually infer the dynamics. In the explorative work, we fit a dynamic model with a stochastic ODE, where a state transition is composed by two parts. The first part is its intrinsic decay, and the second one is driven by a Wiener process. By optimizing the loss function, which is defined as the exponential weighted sum of the difference between fitted covariance matrix and the empirical covariance, we can come up with a value of this C, an estimation of C, and the covariance structure sigma. Next, by adapting the stochastical ordinary differential equation to a dynamic system, we assume that the state transition part remains the same, and the noise propagation term represents how each region will react to the input, because This is because in the original stochastic ODE, the relationship among regions are represented by this covariance structure. So if we have an input or outside input on the specific area, that one will also be propagated to other regions. Thus, we need to have a constraint here instead of allow it to change freely. Okay, but after setting the network, or after setting the system, we can then define the minimal control set as the minimal possibility to make the whole system controllable, that is of full rank. As we discussed before in our structure contributed work, if the network is very dense, actually theoretically it's controllable from even a single node. However, in practice, the computation may be yearly, so here we adapt some different way so that the minimum of eigenvalues would be higher than a threshold. And we find that the minimal control set is actually more likely to distribute it broadly. However, it still accumulates on certain area, for example, those supramarginal area and somewhere in the visual cortex. This is consistent with our discoveries for the structure controllability, where the minimal or the efficient control set is defined with optimal trajectory. If you're interested, you can maybe refer to our optimal trajectory in your image. After quantifying the minimal set, we also look at the relationship among the measurements. In our previous work, we find that the model contributed and the contributed, they are actually very significant and negatively correlated. And the weighted degree is almost strictly correlated with the average contributivity as well. For the structural one, we tested its relationship with structure contributivity, with the weighted degree and the strength of the transition matrix, that is the Jacobian. We find that it's inversely with the Jacobian, but has no straight relationship with the connectivity. And for the measurement, globally, we find that if we control every region at the same time or control one region at each time, the property actually display quite different trajectories, where if we control everything, the two measurements are negatively correlated, and if we control from a single region, since everything is driven by a single element, then the two contributed measurements tends to quantify in the same thing. Okay, that's it. Well, welcome everyone to visit us in Chengdu. We have very nice campus and pandas, but the pandas are not in the campus. And we have not a lot, but we have postdoc and faculty positions open. Thank you.